So today we have like three or four smaller topics to cover. So the first thing that we're going to talk about is source combinations. So essentially, this is us. Sorry, what was that from Zoom land?
Sorry, sir.
So we are going to establish rules for combining multiple voltage sources or multiple current sources, go away, AVG, into a single equivalent voltage source or current source here. Okay. So we're going to start with the one that we're probably the most familiar with, which would be voltage sources in series. So if you have ever changed the batteries in a remote control or anything like that, you have applied voltage sources in series. So your battery pack for your Engineering 120 robot was literally a set of voltage sources in series. So let's consider a case like this where we've got a 5-volt source in series with a 9-volt source in series with some resistive load, which I'm just going to leave that as just an arbitrary resistor RL. And then over here, I'm going to have yet another voltage source, and just for the hell of it, let's make this guy 7 volts. Okay. I'm going to define the voltage drop across our load resistor as VR like so. And what we're going to figure out using Kirchhoff's voltage law is what the equivalent voltage that our resistor sees by that combination of sources. Okay. So this is going to be fairly straightforward. If we apply Kirchhoff's voltage law around this loop, I'm going to start in the bottom left-hand corner and just go clockwise. What we'll get is negative 5 volts minus 9 volts plus the voltage drop across our resistor plus 7 volts is equal to 0. And rearranging this, we would find that the voltage drop across our resistor, which is going to be the same as the equivalent voltage supplied by all of our sources, will just be 9 volts plus 5 volts minus 7 volts, if my math is correct, is equal to 7 volts here. Okay. So what I want from you guys to glean from this is that whenever we have two voltage sources having the same polarity, like the 5-volt and the 9-volt source, okay? And I'm saying that they have the same polarity because when we apply Kirchhoff's voltage law around that loop, we hit the minus sign first on both of them. Those guys get added together. Whenever we have a voltage source of the opposite polarity, so when we were doing KVL around this loop, we hit the positive polarity first on the 7-volt source, that guy wound up being subtracted, okay? So same polarities add together, opposite polarities subtract. Okay. So what that means for us is essentially we could redraw this circuit as our equivalent voltage source connected to our load resistor. So here's RL. And this is the VR that we just found. Notice that we got a positive value for the voltage VR when we solve for it, which means that this equivalent voltage source needs to have the exact same polarity, right? So positive polarity on top, negative polarity on bottom for both. And this is our VEQ is equal to 7 volts over here. If we had followed our loop in the counterclockwise direction, we should have gotten the exact same result, and we should be able to lump that into an equivalent circuit in the exact same way. So I know this was very brief, but is there any question about combining voltage sources in series? So if not, I want to ask you guys a question to help kind of put this in context of why it might be important, okay? So if you put the battery or one of your batteries in your battery pack backwards, what would happen? It wouldn't work. So let's talk about why it wouldn't work, okay? So we had a system where we had, and this is going to be a really shit drawing, but it'll be okay. So here was one battery, right? And this is the terminal of our battery pack. Here's the minus terminal, here's the plus terminal. Then this guy was connected to the minus terminal of another battery. Which was connected to the minus terminal of another battery. Let's see, minus, plus, I need two more batteries here. So across this guy, we should have gotten somewhere in the ballpark of 9 volts because there were 6 AA batteries connected in series, each of those batteries providing 1.5 volts of electric potential, right? Well, if we ever flipped one of those guys, then essentially those two batteries are canceling each other out, okay? So we would have had 1.5 plus 1.5 plus 1.5 minus 1.5, and then plus 1.5 plus 1.5. So we would have only gotten 6 volts out of this battery pack if we flip one of the batteries. The Arduino is designed to work from about 7 volts to 18 volts. So that's why nothing turns on, right? So if you ever put one of the batteries in backwards, it's not going to work correctly because you're canceling out part of the voltage that you're trying to apply by putting those two batteries in series having the wrong polarities, okay? For what it's worth, there's also some electronics inside of your devices that will only allow the batteries to be configured in one direction. So they have what are called diodes, which are essentially unidirectional valves for current flow. You guys might have, or you should have dealt with diodes a little bit with your canister oven project and your relay and all of that kind of good stuff. See some grimacing on your faces like you don't remember what they do. That's perfectly okay. Just know that if you put a voltage in the wrong direction across a diode, it literally stops current from flowing, okay? So that's why there is a very clearly indicated plus and very clearly indicated minus sign on the overwhelming majority of electronic devices because they have diodes and things like that in them. And if you put the batteries in, even if they're all in series correctly, but if you put them in of the polarity it's not expecting, those diodes will prevent current from flowing through the device as well. Okay. So this was batteries in series. I don't think there was anything particularly difficult about this. So we're going to move on to the next thing, which is going to be a little bit stranger. That'll be voltage sources in parallel. Okay. So before we talk about how we're going to treat voltage sources parallel, I want to ask you guys a question. Can you think of any examples where you might see voltage sources in parallel? Yes. So larger scale battery packs, absolutely. So like the battery energy storage systems that I help a company in Bossier City to design, for sure. A thing that's probably a lot more frequently seen, especially nowadays, would be solar panel arrays, right? So typically speaking, a solar panel array can produce a certain amount of voltage and they are rated for a certain amount of power. So if you want more voltage than a single solar panel can create, you might put two solar panels or three or four solar panels in series. They'll just combine together just like batteries and all of that kind of good stuff. But if you want that solar panel array to be able to handle more current so that it can power your entire home or something like that, you're probably actually going to have to put some of those strings of series connected solar panels in parallel with other strings so that the overall power handling capability of the array meets the needs of the load that you're trying to supply. Okay. So let's look at this as follows. I'm going to have, let's just say, a 9-volt source connected in parallel to some arbitrary load resistor, RL, and that's going to be connected in parallel to yet another 9-volt source, like so. Okay. And I'm going to define the voltage drop across my resistor as positive polarity on top, negative polarity on bottom. And what we're going to do is we're going to do KVL around this loop. And we're going to do KVL around this loop. And finally, we're going to do KVL around this loop. And we're just going to check how things work out here. So around our blue loop, what we should get is negative 9 volts plus VR is equal to 0, which tells us that the voltage drop across the resistor is 9 volts. Nothing particularly wild or crazy there. If we do KVL around that green loop, we would have negative VR plus 9 volts is equal to 0, which we could once again solve and say that VR is equal to 9 volts. So those two things agree with each other. And just as a last completely useless sanity check, if we do KVL around our purple path, we would have negative 9 volts plus 9 volts is equal to 0, which doesn't really tell us anything, but we can objectively see that that is a true state. Okay. So we have three mathematical statements here that agree with each other. Okay. So you may be thinking to yourself, well, what the hell was the point of this? And that's a pretty fair question. Okay. So what are these two 9-volt sources doing in this case? They're sharing the amount of current that's flowing through the resistor. So by putting these two voltage sources in parallel, we are lowering the amount of power that each one of them has to individually supply. It's just being split evenly among the two of them. Okay. And we could see that really easily by figuring out, applying KCL at this node right here, right? So this is the current that's flowing down. Obviously, there's just 9 volts over whatever VR is. Well, half of that current's going to be coming from this side, half of that's current going to be coming from this side because those voltage sources are identical, okay? So this is a situation that we could just as easily replace with this circuit. So whenever I have multiple voltage sources that are connected in parallel and they all supply the same amount of voltage, I can just replace it with a single voltage source that's doing all of the work. It changes nothing about the behavior of the circuit whatsoever. So that's kind of boring. But now let's consider a case where my voltage sources are unequal. So let's say that I have a 9-volt source connected to some load resistor. And on the right-hand side, I have an 8-volt source connected to that same load resistor. And once again, I'm going to write those 3 KVL equations, and it should be very obvious that things are not going to match up. So if we write our KVL equation at blue, like we did earlier, we'll get negative 9 volts plus VR is equal to 0, which rearranging tells us that VR is equal to 9 volts. If we do KVL around our green path, we're going to have negative VR plus 8 volts is equal to 0, which tells us that VR is equal to 8 volts. A little bit problematic because we have 2 different KVL paths telling us VR has 2 different values. And then to really explain how messed up this is, if we do KVL around our purple path, we have negative 9 volts plus 8 volts is equal to 0, which is objectively not true. So I could connect a circuit like this using one of those power supplies in this room. I could physically do this all damn day, okay? Now, if I do physically set up a system like this, chances are the wires that I'm going to use are going to get really, really hot, because essentially what's happening here is that our model isn't taking into account that our wires do have some amount of finite resistance, and they will wind up absorbing that potential difference, okay? So from a pure circuit analysis standpoint, we just can't deal with this. It looks like it's breaking the laws of physics, and there's nothing that we can do because we have an imbalance in energy transfer. That load resistor RL can't have 9 volts over it and 8 volts over it simultaneously. That just breaks how everything works because we're either creating energy or destroying energy to make that disparity happen, okay? In practice, if we were to do something like this, like I said, our wires are going to get really, really hot because they have some amount of resistance that's going to take up that potential difference. And so it's going to push as much current out of those batteries as possible in order to make that voltage drop happen, okay? So it's really unsafe, but it can be physically done. So let's just recap these things really quickly. Whenever we see voltage sources in series, whenever they are of the same polarity, you add them together. Whenever they have an opposite polarity, you take the difference. Whenever we have voltage sources in parallel, if they have the exact same voltage, you can just treat it like a single voltage source and go on about your day. And if they have different values for the voltage sources, we can't do anything. So we have to stop what we're doing and just, we can't solve that problem. Okay, it's beyond the scope of what our model can do. Yes.
The voltage sources are like the same magnitude but different polarities.
So if I had a 9-volt source positive polarity on top in parallel with a negative 9-volt source positive polarity on bottom, those are the same voltages, right? Because I can swap the polarities by swapping the sign on the magnitude. But if I had 9-volt in parallel with -9, where positive polarities were both on top, that's breaking the system again. Now, for what it's worth, other than today, you will never see a situation to where you have voltage sources in parallel that have different values. I'm just showing you that if you were to ever see it, there is a problem and you can't really use circuit analysis to deal with that system. Okay. So now we're going to talk about combining current sources. We're going to start with current sources in parallel. So let's say that I have a 5-amp source direction up in parallel with a 2-amp source direction down. Here's my arbitrary load resistance. And let's say that this is a 3-amp source direction up. And I'm going to define my resistor current like so. So much like before, we're really just seeing what the total amount or the net amount of current that this resistor sees, and we're going to treat that as if it were provided by some electrically equivalent current source. So I'm going to apply KCL at the top node, and I'm going to say that currents that are exiting the node are positive and currents that are entering the node are negative. So that would look like KCL number 3 at the top node, right? So since the 5 amps is entering, that's going to be -5. The 2 amps is exiting, so that's going to be +2. IR is exiting, so that'll be plus IR. And then 3 amps is entering, so that'll be -3. Set this equal to 0. And we rearrange to solve for our resistor current. And that should look like 5 amps minus 2 amps plus 3 amps is 6 amps in total. So that is the equivalent current seen by our resistor. So we could redraw this circuit. So let's see. So here's RL. Here's IL. I'm going to erase this arrow. I'm going to replace it in just a moment, but I want to explain where that comes from. And then also another way of thinking about it, right? So we defined IR in the above picture as flowing down through the resistor, and I've defined IR as flowing down through the load resistor RL in my electrically equivalent circuit as well. Since we found that the equivalent current of 6 amps was positive, then that means that we need to draw our current source of 6 amps in such a way that the current IR is positive 6 amps flowing down, which is why I've chosen that direction for the arrow. Another way to think about this, and this is a little bit easier to wrap your head around than figuring out the polarity for the voltage sources, in my opinion, is that if we start with the up direction, so what we're doing is we're adding current sources that are in the same direction, and we're subtracting the current sources that are in the opposite direction, okay? So if I start with the 5 amp source on the left-hand side as my reference, and I'm saying that's what I'm going to consider to be positive, then everyone that's positive just gets added to that. Everyone that's in the opposite direction that gets subtracted from that. And then we're going to have the same arrow for both of our current sources. So if I'd started with the 2 amps as the reference and said, all right, so I'm going to have 2 amps minus 5 amps minus 3 amps, then that would look like negative 6 amps direction down. All right, so this is how we treat current sources in parallel. Again, they're in the same direction, we add them together. They're in the opposite direction, we take the difference. Okay. Current sources in series can be well behaved or terribly behaved, much like we saw voltage sources in parallel. So let's consider a simple case where I've got a 2 amp source in series with some arbitrary resistor RL in series with yet another 2 amp source. Okay. So it should be fairly obvious. Oh, and I'm going to define my resistor current as flowing from left to right through this resistor. Okay. So it should be fairly obvious that this system has 3 nodes, and I'm going to identify them really quickly here. So we've got a node at the top left, a node at the top right, and a node at the bottom. And we are going to apply KCL at each of these nodes. And we're going to do this the easiest possible way. So I'm going to say that the current flowing into the node is going to be equal to the current flowing out of the node. Okay. So at the blue node, the current that's flowing in is the 2 amps. And the current that's flowing out is our resistor current, IR. And so that's our first KCL equation. Okay. And we can figure out pretty easily just by swapping that guy around, IR is 2 amps. Applying KCL at the green node, IR is flowing into the green node, and that 2 amp current source is flowing out of the green node. So once again, we see that IR is equal to 2 amps. Both of those things agree with each other. Everything's great. And just for the hell of it, even though it's providing no real value here, if we do KCL at the purple node, we can see that 2 amps is flowing into the purple node from the current source on the right, and 2 amps is flowing out of the purple node from the current source on the left. And since 2 amps is equal to 2 amps is an objectively true statement, I'm just going to put a check mark by that. So we can see that all 3 ways that we've checked this out agree with each other. So this is perfectly fine. And much like we had with voltage sources in parallel where they had the same polarity and magnitude, we could just replace this with a single current source that's providing all of the power to the system, right? So that would be electrically equivalent to literally just a 2 amp current source connected to an arbitrary load resistor where our resistor current is defined in this direction. Okay. So much like we saw earlier, we can break this by having the current sources with different values. Okay. So if we had a 2 amp current source here, our resistance RL, and a 3 amp current source here, it should be incredibly obvious that this is not going to work correctly. But just to beat this to absolute death, I'm going to go through and apply KCL at each of those nodes just like I did a moment ago. So when we do KCL at our blue node, we get 2 amps is equal to IR. When we do KCL at our green node, we get IR is equal to 3 amps. So obviously IR can't be 2 amps and 3 amps at the same time. And then once again, doing KCL at the purple node just completely and utterly makes this look ridiculous, because we would have 3 amps flowing into the node is equal to 2 amps flowing out of the node, which violates physics. So whenever we have a situation like this, where we have 2 current sources in series, and just for what it's worth, we're never going to see that again after right now, 2 current sources in series where the values of the current sources are not the same, we can't do anything with this. I can't even figure out how the hell we could even physically connect something like this. Like, this just literally does not exist. Just wanted to show it to you just in case. So how do you guys feel about combining sources, voltage sources, current sources? Doesn't seem particularly difficult, right? All right, so let's take a look. Adam, would you mind helping me to distribute these? We're going to take a look at ITA problem 1 together, just as some practice about combining current sources. I think I printed out maybe 5 less copies than there are people in class, because I know some people do it on their tablets or whatever. So if you don't need one, tell them you don't need one, please. So. And thank you, Kason, for helping to distribute them as well. My bad. Thanks. Yeah. All right. So let's take a look at this circuit, or we will as soon as Adam and Payson have a moment to sit back down. All right. Yeah. Thank you. Okay, so we have what looks to be a relatively complicated circuit here. I'm telling you explicitly that we're going to wind up using current source combination techniques here in just a couple of moments. Our ultimate goal is to figure out that voltage drop Vx, which I have defined as the voltage drop across that dependent current source on the left-hand side. But because all of those elements on the left-hand side are in parallel, it's also the voltage drop across the 10 kilo ohm resistor, as well as those 2 independent current sources. Okay. So essentially, what we're going to do is we're going to figure out what Vy is, so we can plug that value into that dependent current source on the left-hand side, and then combine all those current sources together and use Ohm's law to figure out the voltage that we're looking for. I think that is the most efficient path to do this. So does anybody have any thoughts on how we might determine the quantity Vy in this circuit? Sorry, what was that? we can just use Ohm's law. So Ramon, tell me what numbers to put into my Ohm's law relationship here, please. -2 milliamps times 1 kilo ohm. Okay, so before I calculate this, and it's very obviously going to be -2, do I need to add a negative sign or anything, or am I good? Is my Ohm's law set up correctly? So the current is flowing into the positive polarity terminal, so I just leave this alone. Okay. So this is going to come out to be -2 volts. Anybody have any beef about that? Okay. Now, one question that I get from you guys a whole hell of a lot is what's going on with this guy right here. So I'm going to answer that for you guys, and it'll be pretty much the same for every time you see something like this. Okay. So I'm going to say, and I'll prove it to you in a moment, that there is going to be no current flowing through that small section of the circuit there. There's obviously no voltage drop across it, or hopefully you guys can recognize there's no voltage drop across it because it's a wire. And since the resistance of a wire, or the resistance of a short circuit is 0, Ohm's law tells us that the voltage drop across it will always have to be 0. The thing that's a little bit harder to swallow is that there's no current flowing through it. So I'm going to prove that using Kirchhoff's current law. So if I look right here, I have -2 milliamps of current flowing out that's being pushed in that direction by that source. Can we all agree with that? Okay. All of that -2 milliamps of current flows down through this resistor. So I have -2 milliamps of current entering that node and -2 milliamps of current exiting that node, which means the current that's flowing in this direction, according to Ohm's law, has to be 0 amps. And obviously, if I change that arrow in the opposite direction, it would still come out to be 0 amps because there's no way we can slice -2 isn't equal to -2. Okay. So no current's going to flow through that little path there. So essentially, the right-hand side of the circuit and the left-hand side of the circuit are operating independently of each other. The only thing that's causing that dependence is that dependent source. We've already figured out what that voltage Vy is, so we can now just completely ignore what's going on the right-hand side because we're done with it. Okay. So I want to ask you guys another quick question here. What are the units on this 0.03? So we talked about the units on dependent sources. So what kind of source is this? So let's start. Is it a voltage source or a current source? It is a current source because there's a big arrow that's telling me it's a current source, okay? So this is one of the 2 different dependent current sources. Is this a voltage-controlled current source or a current-controlled current source? It is a voltage-controlled current source because I have some scaling factor being multiplied by a voltage. So since this guy is taking voltage in and outputting current, the units of that 0.03 have to be amps per volt. Otherwise, when I multiply something in amps per volt times voltage, I get amps at the output, right? So what's 0.03 amps per volt times -2 volts? Negative 60 milliamps or -0.06 amps, okay? So I'm literally just going to scratch this guy out because since Vy is a known quantity, and I'm going to say that this is -60 milliamps. And since this is now a fixed amount of current, I can just add all those current sources together because they are connected in parallel, right? So what's 12 minus 60 minus 3.5? You guys, I think, have calculators. -51.5 milliamps, okay? So I'm going to have a current source here, -51.5 milliamps. The reason why it has direction up is because I said that 12 up was my reference, and I subtracted the other two that were in the opposite direction from that. Here's my 10 kilo ohm resistor. And lastly, here is the voltage Vx that I'm interested in. And I believe that we can all see I can solve for Vx very easily just using Ohm's law here, right? So Vx is going to be negative 51.5 milliamps times 10 kilo ohms is negative 515 volts. Any questions, comments, or concerns about how we approach that? The logic as well as the circuit analysis that was employed. Adam, how may I help you?
51.5.
Where'd that come from? Add this guy and this guy and this guy together. 3 current sources in parallel. So I said 12 up minus 60 because that guy, so 12 plus negative 60 minus 3.5 because the 3.5 is in the opposite direction. Yes.
You're assuming 51.5 milliamps is going up because that first.
I'm assuming negative 51.5 milliamps is going up because I treated the 12 as my positive reference. Okay. Let's circle back around to lecture stuff. So I feel comfortable with source combination. Hopefully you guys do as well. You'll practice it more on homeworks and stuff like that. So now what I want to talk about is voltage division and current division, okay? So for those of you who didn't have me as your 120 teacher, you're about to feel really cheated. So voltage division and current division, which I'm going to talk about here in a few minutes, is a shortcut that we can use to calculate the voltage drop across a resistor without having to bother figuring out what actual current flows through it, okay? We're going to start off with the most simple case, and then we're going to show how we can adapt it for much more complex things, okay? So I'm going to start by defining the rules for voltage division. And this is going to look incredibly similar at the very beginning to how we defined how resistors combine in series, okay? So I'm going to start with some resistor R1 in series with some resistor R2, all the way out to some resistor R sub n, like so. And this series combination of resistors is part of some larger circuit, okay? So assuming that our circuit is on, we should expect to see some total voltage drop across all of those resistors in series, as well as some current flowing through all of those resistors connected in series. And I'm going to define the voltage drop across each resistor such that our current is flowing into the positive polarity terminal. So that means this voltage resistor R1 will have a voltage drop V1, positive polarity on the left. R2 will have a voltage drop V2, positive polarity on the left. And our resistor R sub n will have a voltage Vn, positive polarity on top, like so. Much like I did on Wednesday, I'm going to just say that the total voltage drop is the sum of all of the resistor voltage drops. That's nothing more than an application of Kirchhoff's voltage law. So we would have V is equal to V1 plus V2 all the way out to V sub n. And much like on Wednesday, I'm going to use Ohm's law to then say that this is I times R1 plus I times R2 all the way out to I times R sub n, or I times the sum of R1 plus R2 all the way out to R sub n. What I'm going to do now is very slightly different, so I'm not looking for an equivalent resistance here. I'm going to solve for I, and it should be very obvious that the current I in this case is just going to be our total voltage drop across our network divided by the sum of all of those resistors, R1 plus R2, all the way out to R sub n, like so. And now I'm going to solve for the voltage V1 or V2 or V3, all the way out to V sub n, it doesn't really matter. So using Ohm's law, the voltage V1 should just be I times R1. Well, if I substitute in my value for I, that's actually going to be V, the total voltage, times a ratio of resistances, where the resistor that I'm interested in, R1, is in the numerator, and then the sum of all of those resistors in series is in the denominator. And if I wanted to do the voltage V2, how would this change? The R1 would be replaced with R2. If I wanted to find R7, R1 would be replaced with R7, okay? So in general, we can say that the voltage drop across the kth resistor in a series combination of resistances, where the kth resistor is just whatever one I'm interested in, is going to be my known voltage multiplied by R sub k over R1 plus R2 all the way out to R sub n, which is the same thing as V known times RK over the equivalent series resistance. Now we're going to work some simple example problems to kind of show you how this is applied. So let's start with something like this. Let's say that I've got a 15-volt source connected to a 10-ohm resistor, an 8-ohm resistor, and a 7-ohm resistor. And I want us to find two things: the voltage drop across the 8-ohm resistor with positive polarity on top, and the voltage drop across the 7-ohm resistor with positive polarity on the left. So I'd like your assistance in setting up these equations, okay? So what's our known voltage here? The 15 volts, okay? So when we're solving for the voltage V8, that means that we want the 8-ohm resistor in the numerator because that's the one that we're interested in finding the voltage drop over. So I'm going to put 8 ohms up here. What should go in my denominator? 10 plus 8 plus 7. Okay. And I'm going to throw this into my calculator real quick. Well, 15 times 8 is 120 over 25. It's going to be just shy of 4.8, I think. Yep, 4.8 volts. So before we move on from this example, anybody have any question where any of these numbers came from? Should be fairly straightforward. Okay. So what's going to change when I calculate the voltage V7? So it's going to be negative, and we'll talk about that in a moment. And the value of the resistor in the numerator is going to change because I'm interested in a different resistor, right? So everything else is going to be the same. So I'm going to put my 15 volts here. 7 ohms will go here. And then 10 plus 8 plus 7 will go here. And that's going to be, let's see, 105 over 25, 4.2. If my mental math is working correctly. Hot damn it is. Firing on all cylinders today. Now, Adam suggested, and Gabriel, maybe? What's your name? Carlos, sorry. Carlos also suggested that this voltage V7 is supposed to be negative, and they are both correct, okay? So I want to explain to you why they're both correct, and there's a couple of different ways that we can do this, but I think the most obvious way, if we look back here, when we set up how voltage division works, we had the current I flowing out of the positive polarity terminal of our known voltage. So we're following I as it flows around in this direction. It flows into the positive polarity terminal of the 8 ohm resistor, which is why that voltage division equation got a positive sign. It was flowing into the negative polarity terminal of the 7 ohm resistor, which is why that voltage division equation gets a minus sign. Fairly straightforward, I believe, right? Another way to think about it, if it has the same polarity as the voltage source, it needs to have a negative sign. When we go back up here, all of our resistor voltage drops were defined as having the opposite polarity, right? So as we follow that current around, the current would go, out of the positive polarity terminal of the V into the positive polarity terminal of the resistors, right? So just be careful when you're applying voltage division and make sure that the polarity of the resistor you're finding the voltage drop across makes. Yes, Adam.
So what's the polarity of the 10 ohm resistor?
Whatever we choose for it to be. So if I chose it with positive polarity on the left, it would be whatever 15 minus 4.8 minus 4.2. So let's see, 6 volts. If I chose it positive polarity on the right, it would be negative 6 volts. Because they have to add together to make 15. Yes.
The resistors are connected in anything other than series.
So that's what we're about to figure out. So the way voltage division in its most fundamental form is meant for you to be able to find the voltage drop across any individual resistor as part of a series combination of resistors, right? So if that's all it could do, it wouldn't be worth learning, in my opinion. Like, we're not going to see things like this that are this simple that often. So now I want to explain how we could possibly adapt it to other things. So there's going to be stuff that you've seen in your previous homeworks from other classes, stuff that you'll see in homeworks in this class, to where we can use voltage division to cut out a couple of steps of things. Okay. So let's say that we've got something like this. Here's a 10-volt source. I'm trying to decide whether or not to throw you guys a curveball. I don't think I'm going to do it yet. So thus far, everything looks exactly the same as what we've done. But now I'm going to add this other path over here. And I'm just going to arbitrarily make some stuff up here. So let's say that this is 15, 20, 25, 30, and 35 like so. And what I'm interested in is this voltage, which I'm going to call Vx. And as a secondary, this voltage that I'm going to call Vy. Okay. So this is more in line with things that you guys may have seen in the 120 series where problems were starting to get a little bit harder. Okay. So I'm going to show you that we can use voltage division for this situation to find for Vx, and we can actually use voltage division to find Vy as well. Okay. So what we're going to do in order to find Vx using voltage division, so I've got a 10-volt source in series with a 15 ohm resistor, and then that network of resistors, and then that's in series with a 35. So if I can make everything to the right of this dashed line look like some equivalent resistance, that will be in series with the other part of the circuit, which will allow me to apply voltage division to figure it out. Well, what is the equivalent resistance of everything to the right of that dashed line? To me, that's just 25 in parallel with 50, right? So what's 25 in parallel with 50? Twenty-five times 50 over 75. I'm just going to do it in the calculator before I screw that up. Fifty over 3. Yeah, so 16.667. Yeah. So we would have 10 volts, 15 here, 50 over 3 here, 35 here, and this is the Vx that we're looking for, right? So we could say that Vx is going to be 10 volts times 50 over 3 ohms. Actually, that looks too much like it's 50 divided by 3 ohms, not 50 thirds of an ohm. Sorry. And throwing this into my calculator. If I put this in correctly, I got 2.5 volts. Now, realistically, I am far too lazy to actually redraw this damn thing and do it this way. So what I would actually do when I get comfortable with it is something like this, where I would say that Vx is 10 volts. And then in my numerator, I would have 25 ohms times 20 plus 30 ohms over 25 ohms plus 20 plus 30 ohms, which is just that parallel combination of the 25 and the total resistance of 50 we see on the far right-hand side. And then here I would have my 15, exactly what I have in my numerator here. And then my 35 goes over there. Right. So I just throw that all in my calculator without bothering to redraw it because I'm comfortable enough to see that I'm just treating everything on the right-hand side as a single equivalent resistance. So I'm just going to put that equation directly into my voltage division relationship so that I can cut out an extra step there. Okay. And quite obviously, I believe we'll get the exact same result of 2.5 volts. So how would I find Vy now? I can do voltage division again, because I know that the potential difference between this node and this node is 2.5 volts. So that's a known voltage. So Vy would literally just be Vx as my known voltage times 30 over 20 plus 30. So that's going to be 3/5 of 2.5. So 3/5 times 5/2, 15 over 10, 1.5 volt. Right? So double voltage division to get that voltage Vy. Anybody have any questions, comments, or concerns here? So I want to be very, very clear about this. This only works when we have just voltages in our system, right? So if I had a current source in here, that automatically messes up my ability to do any type of voltage division. Yeah, messes up just the ability to do voltage division at all. So it only works whenever we have voltage sources and all that kind of good stuff. All right, any questions regarding voltage division before we move on to current division? Do you want to see me work, I don't know, more examples? Yes. 20 plus 30. Sorry, my penmanship is shitty. So to be clear, I'm able to do that because the 20 ohm resistor in series with a 30 ohm resistor is between the node that I've labeled in green at the top and the node that I've labeled in blue at the bottom. So since I have a known voltage across that, which is just Vx, I can do voltage division again because I have a known voltage being applied across two resistors in series. Yes.
You don't need to.
So fantastic question. The voltage isn't splitting across the 25 ohm resistor. We know that that total voltage is 2.5. So we figured that out in our first step. So I need voltages in series in order for it to split. All 2.5 occurs across that 25 ohm resistor, so it doesn't have an opportunity to split. So it shouldn't show up in my voltage division relationship. That essentially was the thing that I was going to try to throw you guys as a curveball, is just putting something directly in parallel with the 10 volt source, but I got to answer that question anyway, so now I don't have to be mean and do it. Any other questions with regards to voltage division? So for what it's worth, if this isn't clicking with you, I would still encourage you to practice it, because in the third part of the class, so let me preface this really quickly. Okay? So Monday, we're going to talk about linearity and superposition. And then Wednesday of next week, we're going to talk about nodal analysis, and Friday of next week, we're going to talk about mesh analysis. Once you guys learn nodal and mesh, that's what you're going to try to do for literally everything. Just, it's the nature of the beast, okay? Nodal analysis and mesh analysis are very, very powerful tools that allow you to set up a system of equations so that you can find all of the voltages in the circuit at once, or all of the currents in the circuit at once, okay? It's great, it's very powerful. I understand why once you learn that, you tend to throw it at everything, because it's just a one-size-fits-all method of circuit analysis. However, the third part of the class, when we're doing our circuit analysis in the frequency domain, we can't really rely on nodal and mesh anymore, because our calculators literally cannot solve systems of equations involving complex numbers. So what we're going to fall back on is Ohm's law, KCL, KVL, voltage division, and current division. So if you don't want to get wrecked on exam 3, this stuff kind of needs to make sense to you. So even if you don't like it, I would highly suggest that you practice it, or you're going to have a really shit time later on in the class. Yeah. All right, now let's talk about current division. So current division is essentially the same thing as voltage division, except for currents when we have resistors in parallel. And when we're setting up the rules for this, it's going to look a lot like what we did on Wednesday, where we figured out how resistors combine when they are in parallel. Okay. So I'm going to start with just a network containing multiple parallel resistances. So these resistors are a parallel network as some part of a larger circuit. So once again, assuming that our circuit is on, I would expect to see some voltage drop across all of those resistors connected in parallel and some total amount of current I flowing into that network of parallel resistors. And we may be interested in finding the current flowing through any individual resistor. So I1, I2, or I sub n, like so. Okay. So applying Kirchhoff's current law to this system, we would have a current I, our total current, is equal to the sum of our resistor currents, I1 plus I2, all the way out to I sub n. Putting these in terms of Ohm's law, we would then have V over R1 plus V over R2, all the way out to V over R sub n, or V times a factor of 1 over R1 plus 1 over R2, all the way out to 1 over R sub n. And now I'm going to solve for that voltage. So that voltage is just going to be my total current I divided by 1 over R1 plus 1 over R2, all the way out to 1 over Rn, which should be fairly obvious, but that's literally just I times Req in parallel. So from here, I can use Ohm's law to solve for that current I1, because it's just going to be V divided by R1. But I'm going to do something a little different here. Instead of doing V divided by R1, I'm actually going to write this as V multiplied by a factor of 1 over R1. And in writing it in that slightly odd form, winds up giving me this result. Well, so when I substitute in V, I'm going to put in my total current, and then I'm going to have a ratio of the reciprocal of resistances. So I'm going to have 1 over R1 in my numerator, and then 1 over R1 plus 1 over R2, all the way out to 1 over R sub n in my denominator. So generalizing this, and I guess I should ask the obvious question, but if we were interested in the current flowing through resistor R2, what would we do? We'd replace the 1 over R1 with the 1 over R2 in the numerator, right? So generalizing this, we can say that the current flowing through the kth resistor is just going to be our known current multiplied by 1 over R sub k divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And this is the same thing. Sorry, I'm running out of space here. I known times Req in parallel divided by the resistor that we're interested in, which I pretty much never use that. I always just use this thing right here anyway. So let's work a quick example or two. let's say that I have a 5 amp current source connected to the 6 ohm resistor, an 8 ohm resistor, and a 10 ohm resistor. And I'm going to define the current I6 is flowing down, and the current I10 is flowing up. And we're going to solve for those two quantities. So using our relationship, I'm going to say that I6 is equal to my known current of 5 amps. In my numerator, I'm going to put 1 over 6 ohms. And in my denominator, I'm just going to put the reciprocal of all of the different parallel paths. So 1 over 6 ohms plus 1 over 8 ohms plus 1 over 10 ohms, like so. Throwing this into my calculator real quick. I get 100 over 47, so a little bit over 2 amps. If I were solving for I10, what would change? So the 1 over 6 would be changed to 1 over 10. And once again, this one is going to have a negative sign in front. Okay. So negative 5 amps, 1 over 10 over 1 over 6 plus 1 over 8 plus 1 over 10. Comes out to be negative 60 over 47 amps. I think it's kind of intuitively obvious why this guy needs a negative sign, but I'll happily explain it, right? So what we would expect is that 5 amp current source is going to push current in this direction, and then it's going to split among those resistors. We would expect it to split down through those 3 paths. Well, I10 was defined in the opposite direction, so we need a negative sign to take that into account. All right, so the very last thing that I want to do is show you how this can be adopted to slightly more complex circuits, okay? So let's say that I have a 3 amp current source connected to a 10 ohm resistor, a 5 ohm resistor, here's a 15 ohm resistor, and here's a 20 ohm resistor. And I want to find this current, which I'm going to call IX, okay? So I want to point something out here. Current division is how we find the current through resistive branch when we have a known current flowing into multiple resistive branches that are in parallel. This circuit looks like it doesn't have literally any resistors in parallel, okay? But I think we all know, at least I certainly hope we all know, that 15 in series with that 20 is in parallel with that 5 ohm resistor, which is what's going to allow us to use current division in this case. Okay. So I'm going to write down the equation that I would use here, and then I'm expecting a question. We'll see if you guys ask it. So my known current is 3 amps in my numerator, I'm going to have 1 over the total resistance of the branch that I'm interested in finding the current through. So that's going to be 15 plus 20. Because it's 15 plus 20 that's in parallel with the path containing just the 5 ohm resistor. Throwing this in my calculator. Let's see, 15 plus 20 is 35, just being lazy. I wound up getting 3/8 of an amp. Anybody have any questions? Does anybody what's the question?
What happened to the 10 ohm?
What the hell happened to the 10 ohm resistor? Thank you. That is exactly the question that I'm looking for. Okay. So how much current flows through the 10 ohm resistor? 3 amps, all of it. So it hasn't had an opportunity to split yet. So why should it show up in my current division equation, right? So essentially what I'm saying is that I know that 3 amps flows through this resistor. So it's this 3 amps that's already flown through the 10 ohm resistor that's dividing between those two parallel paths. Does that make sense? So if all of the current flows through the resistor, it shouldn't be part of the current division equation because it hasn't divided. Just like up here, that 25 ohm resistor didn't show up in our voltage division equation for VY because all of that voltage drop occurred across the 25 ohm resistor. Okay. All right, that is enough out of me for today. We do have a mini lab for today, but honestly, the class meeting on Monday is also going to be relatively shortish. So if you don't finish the lab today, you can finish it on Monday pretty easily.